being here.
Oh, thank you. Thank you very much. Good morning. As he mentioned, my name is Bill Sublette. I'm a geotechnical engineer and what I call a geocontractor. So I also do underpinning the structures, shoring, and I also make this clay, or chemical to stabilize swollen clays. So there's a variety of things I'm involved with, but what I'm going to talk about today is this chemical AGSS-ICS. AGSS stands for Advanced Geotechnical Soil Stabilization, and ICS is Ionic Clay Stabilization. And we'll go through some case histories. I'll do a little bit of the theory, a little bit on clays and so forth, and how this actually works. And then we'll get into some case histories after that. And I'll try to leave some time at the end, for any questions or anything like that. All right, bear with me, it's coming up differently than what I normally see in a PowerPoint. Okay, so what is AGSS, ICS? It's basically a hydrogen. By the way, can you guys hear me okay? Am I too loud, too weak, or what? You're okay? Okay. AGSS ICS is a hydrogen ionic chemical stabilizer that is used in treating swollen clays. The original ionic stabilizer was, from what I've gathered in research, was developed around 1957 by this two fellows named Conrad Silicon and Lee Reynolds. Lee Reynolds was a brilliant guy. He was a consultant with Werner von Braun. He was into chemistry and physics and so forth on the space program and all that. But anyway, they came up with this. The idea initially was to try to dry out some of these saturated fields. There were clays and football fields, golf courses, and things like that just you couldn't get rid of the water. And that's how they stumbled onto this. And then basically they developed a company. And after that, they got into more road work. And most of it is actually overseas. There was a lot of overseas work. Did a lot of research out of Brazil, Germany, South Africa, extensive amount. Unfortunately, so much of that has been lost with time. They have both passed away, but I know the son, Gary Silicon, and that's where I came across some of the history, you might say. But how I was introduced to it was in 1972. Nixon was pulling all the troops out of Vietnam. They had too many first lieutenants, and they gave me an early out, go back to graduate school. So when I went back to University of Arizona, the first class I had was what's called physiochemical soils. And it was a 5-unit course, 2 semesters, so it was 10 units altogether. And I mean, it was quite a course. There was only 3 universities at that time that even offered anything like that. It was Mitchell at Berkeley, and then R.L. Sloan in Arizona, where I was, and then some guy in McGill University. I don't remember his name now. But it was quite a course. I mean, there was all this equipment, exotic equipment. It's a very expensive class to offer, and you have to have a pretty broad knowledge person teaching it. But anyway, so we got into that class, and I think he had some sort of a grant, but we were going to look at all these soil stabilizers, mainly for clays, that exist in, which are pretty much the same ones that exist now. And this being one, the Ionic, that was produced by Silicon and Reynolds, and it was called, at that time, I think, Road Packer 235 or something like that. It was some unusual name. And then there was, the potassium ion, that was more out of Mitchell, and eventually he sold, I guess that was sold to Hayward Baker. But then there was, lignans, fly ash, lime, cement. I mean, there was a multitude of types of stabilizers that we looked at. And the first thing we did swell tests on all of them. And this, actually, the Road Packer, this particular chemical, which you'll see in a little while here, hydrogen is a key part of it. It really produce the best results. But we still went ahead and did X-ray diffraction, scanning, transmission electron microscope, all that stuff, nuclear spin, the whole thing. I mean, we looked at all this for 2 semesters, 10 units. And at the end of the whole thing, this is what that we found was the best. Unfortunately, I didn't stay with this. I went into numerical modeling, and that's where I ended up, doing my PhD work and so forth, and numerical modeling, gabion and retaining walls. But, I'd say about 9, 10, 11 years ago, I got back. I was introduced to this by Gary Sullivan again. He came by and he was talking to me, trying to get me to spec in this chemical and so forth. And I said, listen, I know this stuff works, but you could be a snake oil salesman. And this is the biggest dilemma of this stuff. There's been so many snake oil salesmen out there, and I have to carry that baggage around all the time. So, that's a problem. But anyway, so I told him, listen, you gotta prove it out. So after about a year and a half, I finally believed his chemical, and I knew what the constituents was anyway from before. So that's how I got into it. And it's been sort of gradually going along. I do a lot of stuff, but this is just one thing. So basically, the ICS will eliminate the natural swell potential of the expansive clays, and it's a permanent effect. The changes in the clay particles lattice will actually do, the changes are due to isomorphic substitution and cation exchange. And these changes, this guy out of Sakura out of Texas A&M, he did some research on it. And he found that it was actually degrading the clay lattice structure, the actual crystal structure of the clay lattice. And so when you start degrading clay lattices, it becomes permanent. You're not going back the other way. There's just no way you're coming back the other way. So it's a permanent type thing. And so anyway, another benefit it has is that it reduces soil suction as well as increase in strength. Reducing soil suction is really important. I mean, if you're on roads, for instance, and you have water off the sides and so forth, if that clay is under the road in the subgrade, it's just going to keep sucking and sucking. But if you can reduce that soil suction about 10 times, you can minimize the amount of water that's going to be pulled underneath the road. So it's not only reducing the swell potential, it's also reducing the soil suction. And there's some increase in strength. We're doing more research on it right now. My son just graduated from UNLV in civil engineering. And so he's working with me now, and we're developing this further, actually, to increase the strength. The strength is increased, but not that much. We want it more. And also we're developing another chemical for cohesionless soils that will be a plastic polymer. And I'm not going to get into details on this because we're still developing, but the bench testing that we're doing right now is pretty promising. But we got to do it where it's economical. Of course, that's always a problem. Is it going to be economical? This is economical, but that plastic polymer, we got to make that economical. I think we will. Anyway, so continuing on here. And by the way, down here at the very bottom, you see CST, and then AGSS ICS. AGSS ICS, that's me. CST is concrete stabilization technology. I'm sorry, and they're the company that and they're all throughout the Rocky Mountains, and they're the applicator that I sell to. I identify them as the applicator. I mean, they're very good. They pay attention to detail, and they're very concerned about quality control and quality assurance. And so, I like them. So this PowerPoint is, we've used that with CST. I've got in the rest of the United States, other people. Now, what's interesting about CST, this is how it works with them. They do Eurotech, which is an expansive polymer for lifting and stabilizing structures and roads and whatever when they're going down. But when they're swelling, they didn't have anything like this. So that's how I'm getting involved with this Urotech. I mean, Urotech is expansive polymer. I don't do that, but I'm associating myself with the Urotech applicators because they don't have anything for swelling situations. So that's why we're working together with CST and other Urotech companies in the United States. Anyway, so where to use it and why? Yeah, for new construction on subgrades of roads, foundations, slab on grade structures, you know, we can use it in so many places here. But for roads, you know, I was talking with David here earlier, you know, what I see, and this is important, I think, because, you know, and I've designed roads, you know, the sections, and you know, everything's based on the R value and traffic index, all that stuff. But the R value is all about modulus, resilient modulus and strength and things like that. But, you know, it doesn't, you know, where I see the problems on roads, it's not like it's a lack of strength. It's clays, you know, that are going like this. I mean, the roads are, whoa, like this, freeways everywhere. I'm not saying around here because I'm not as familiar, but I know down further south, it's pretty bad. And so this is where I think, you know, a lot of the designers need to consider the clay more and try to, you know, deal with that. But anyway, this is a more economical method than lime. It also, you don't have to treat it. It's a one-time treatment. Lime, you have to treat it. And also lime has other problems. I mean, like down in Las Vegas, they won't let anybody use lime because of sulfates. The calcium sulfate, there's gypsum mines all around the valley. And it has sodium sulfate. Sodium sulfate's unbelievable. It just really blows roads up. But they've had some serious problems down there. And so they won't even let them use lime down there anymore. So anyway, going on here. And then for remediation of existing distressed roads and structures, and you'll see that in a moment. Yeah, I better get cracking here. And because I want to show you this case history especially. So it's fast, cost-effective. If we do injection, for instance, there's no subgrade excavation required. But if you do have subgrade excavation, you don't have to take it away and export it and then pay somebody to take that bad clay and then buy the select fill and bring it back and pay for all that transport and then have all that, you know, let's say, environmental, you know, CO2 and all that, and you're dealing with it on these trucks and everything else. But so there's different benefits, but especially the cost. It improves soil compaction, overall strength. I've already mentioned strength, but soil compaction, it blows these graders away. You know, they sort of resist it. Oh, you know, they don't want to do it, this and that. Just get out there and do it, and you'll see. You'll be able to get compaction like you can't believe. You have no problem getting compaction. And especially if it's been raining a lot, you know, it really helps out. And I'll get into that more here, but does not cause sulfate heave like lime, safe for the environment. I have a risk assessment study available. If anybody wants to see it, I'll share it with you. I mean, there's no problems with this from a health standpoint at all. Best for the environment, environmentally inert product, you know, no heavy metals, dust pollution, you know, it minimizes dust for sure. And whenever there's any dust control spraying, you always have to have the chemical. Don't spray on the raw water. You know, you're working against yourself. Anyway, smallest carbon footprint, and no landfill space consumed for waste soils. Why ionic stabilization works, I'm going to go through this a little quicker here. There's two methods why it's working. One is isomorphic substitution. And it's basically, these clay lattices have a negative charge. And that's what allows them they produce more of a dispersed structure face to face. Flocculants a little bit more like that, edge to face. But they're more face to face because the negativity, and they're just sucking in these water molecules, polarized water molecules. It's better I talk more in detail about that. I'll skip over this right now, but the other method is the cation exchange around the surface. I'll get into that more so we can save time here. But we're trying to basically negate the negativity of the clay particle charge. And all right, so let's go on here. Okay, common clay minerals. The first one is kaolinite. There's basically three common clay minerals. Kaolinite is the first one. It's a 1-1 mineral. In other words, one silica tetrahedral part of the lattice and one aluminum octahedral part of the lattice. And they're 1-to-1. Now, they're the least expansive because the bond, the hydrogen bond and the van der Waals forces between these two parts of these lattices is very strong, and they can't bring the water and it can't expand. But these next two, that's a whole different ball game here. We get into illite. Now it's becoming a little bit more expansive. This is a 2-1 mineral, 2 silica tetrahedral, and 1 aluminum octahedral. That's sandwiched between the 2 silica. And in between here, this area right in here, this is where we call the diffuse double layer. And that's where everything goes on. That's where all is sucking in all this water. And, and you'll see here in a moment here better. And then we have Montmorillonite. That's the big problem. And I think over here near Price, I believe, in that area there, you guys have a lot of bentonite and things like that. I could be wrong on the location of the city, but anyway, that's whoops. What happened here? Jeez. Hold on. This thing got out of control. Yeah, there we go. All right. So basically, this is the worst. Smectite, bentonite Montmorillonite smectite is another name for this type of clay mineral. Now the smectite, and I'll go through this. I won't bore you with this too much, but this shows how it's set up. The Montmorillonite. You have on the top here a tetrahedral wedge, or not wedge. I'm thinking of rock slope stability. A tetrahedral structure here with a silicon in the inside and 4 oxygens around the corners of the tetrahedron. And then you have another tetrahedron right down here, and in the middle here is an aluminum cation surrounded by 6, I think it is, hydroxyls, and they're sharing between the tetrahedron and the octahedron. And then in between the next clay lattice, this is a diffuse double layer, and you'll see this more. This is where all the stuff goes on, and you'll see this here. I'm sort of going fast because I want to make sure. Maybe I'm going too fast here. So anyway, well, let's go on to the next one here. You can see here, this is just another depiction of it. The tetrahedral is here sandwiched in the octahedral, and these are cations in the diffuse double layer zone between there, and there's also polarized water molecules, and I'll talk more about polarized water molecules because that's what's really causing the swelling. You can see here how just the rotational thing, just showing a 3D view. Okay, here's the clay surface on the left side. This is a distribution of ions adjacent to the clay surface according to the concepts of the diffuse double layer. And what we see here, and these are plus cations, and then the negatives are anions. And over here it shows the distribution, the concentration distribution of the cations coming. This is the clay surface coming away. It drops off, and anion starts increasing. So anions are low in here, but greater in the middle. There's going to be another clay lattice over here and this in between in here is going to be the diffuse double layer. And you'll see it better in probably this next slide here. Yeah, here we go. Okay, this is a generalization of what we have here. The scale's not quite right because I had to make it so you could see it. But this is the diffuse double layer. Here's the silica tetrahedral, the aluminum octahedron, and the silica tetrahedral sheets. And then down here is the next lattice down here with the same type of, the 2-1 arrangement. And in between here, this is the diffuse double layer. So this is where it's all happening. And here you see these oblong water molecules here, and they're polarized. Water molecules have a polarity to them. with hydrogen at one end, the positive end, and the hydroxyl at the negative end. So they get polarized, and they start being attracted to that negative. Remember, this lattice is negative. And I might add, I sort of skipped over that too much before, but I might add, it's the isomorphic substitution can cause a negativity inside the clay lattice. And the geometry of the oxygens, let me go back, it's just a second. I was trying to go too fast. But basically, these cations in here, they can be substituted for. And if it's substituted for by a lower valence cation, then you get a negative charge. But in reality, the real negativity of these clay lattices is due to the weathering process. And as the weathering process proceeds, about 30% of these cations in the silicate tetrahedral and aluminum octahedron are missing about 30% of the silicon aluminum cations. And that's what really gives it the biggest charge. So when we say it's isomorphic substitution, it's not like necessarily one cation going in there and kicking out another cation on the inside. It's actually substituting into a void where it's missing a cation. And so that's how we're neutralizing that negative charge, because remember, it's a negative charge that causes all the problems. That's what pulls these water molecules in the polarized water molecules. So the isomorphic substitution negates it, and you're going to see here in a moment how we negate the surface charge, the cation exchange capacity on the outside. Because on the outside, these here are all oxygen, the anions basically, oxygen, negative oxygens, and that produces the negative oxygen due to the geometry of the arrangement, and that adds to the negativity of the clay particle, clay lattice. So let's go on a little bit further here. So going back to this one. So before ionic stabilization, you can see all these water molecules lining up. They're all lining up here, and polarized, growing. They keep growing and growing, and pushing and pushing. And especially if the bonds between the lattices are weak, it easily pushes it apart, like the montmorillonite, smectite. And you also see some cations in here. Here's a calcium here, and here's a sodium over here, and they're dispersed through here. You'll see a few, I don't have any anions in there. I don't know why I didn't put those in there, but there would be more in the middle in here. And so as this thing keeps sucking water, and it just keeps on pushing apart. Now, when we treat it, what we're doing when we treat it, we're negating the negative charge of this clay lattice. And when we negate the negative charge, and we do that by the isomorphic substitution inside the interior of the clay lattice, and we also do it by cation exchange. And how this happens, why we call it the hydrogen ion, is that the hydrogen ions are produced when we disassociate the water molecules into a hydrogen ion, cation, and a hydroxyl anion. When we disassociate that water molecule, those hydrogen cations, they just start sucking into the clay lattice, to the surface here. They don't go inside internally. Those are other bigger cations that go in there. They just come along the side. They're the smallest cation there is. So basically, we can negate the surface negativity of this clay lattice fairly easy by just swamping that surface with these very small but single valence cations. And that there's a high concentration, so the unity there of that charge is quite high, and we can just basically negate that. And so once that happens, then this clay lattice tends to be more of a flocculent structure. It doesn't have that dispersed effect as much. And that's what we see there. So there's two application methods. When we do the chemical itself, there's two methods we normally do. And one's a mixing operation in the field. These are all obviously in the field. And the other is an injection method using hand wands or a rig, a big rig. And these are the two methods how we get the chemical into the clays. The mixing operation is done during grading. And basically, we over-excavate the material to the depth. I'm going to show you some that we've done in different places, but one of the big ones is down Las Vegas, in North Las Vegas. And that one was over-excavated 15 feet because the swell pressures are so high. And there was some higher perched water tables too that they were concerned about. That one I wasn't the geotechnical engineer record on, but I actually did all the testing. We did over 243 swell tests on that, but I'll show you that in a moment. So basically, we over-excavate the soil, and then we come back in 8-inch loose lifts. We mix the chemical in the water pool or the water truck, whatever we have, spray it on there, and then we take a disc. You don't have to use a disc. I wouldn't use a motor grader. Don't let those grading guys talk you into that. Use a disc or use a reclaimer, something like that, or this asphalt zipper that they sell here in Utah. It's a pretty neat deal. I've used it in California. It's real slick, the asphalt zipper. And in fact, it's, I think, produced somewhere around here. But something that can really process that. And I'll tell you a story here, because I was raised on a ranch and a farm in California, and we knew how to deal with clays. We definitely knew how to deal with clays. And we always used a disc, when you really wanted to process it. And when I was younger, I was working for the Army Corps of Engineers, and we ended up getting we'd have these earthwork guys out there doing earthwork. And what I noticed, invariably, they would always have discs when there was clay projects. Now, I don't see very many construction discs out there. This is the best thing. I mean, you can save so much time. You can process it so much faster. But if you're just using a motor grader, it doesn't process it as well, not nearly. That's just some additional information I've come across over the years. Then on the hand rigs and injection wands, these can be used for construction or remediation of existing distressed structures. The large injection rigs can treat up to 10,000 feet per day. The smaller hand ones are much less, but they still can do pretty good. And hand injection is ideal for remedial treatment of existing structures, existing roads, and so forth. And the big ones definitely for roads. And with doing the injection wands, you don't have to over-excavate. You just basically go right through the road and inject it right through the road into the depth you need, and without tearing everything out. So it does save money. The only problem with the injection is you have to rely on soil suction and osmosis to really distribute the chemical. And there is, it takes a while, it takes longer basically. But the results are pretty good though. They're not quite as good as when you over-excavate, but they're pretty good. So here's this is how we evaluate your project. Whenever there's a project, we take a look at it. We want to, get a geotech, look at the geotech report, review that, see what's out there, because everything, it really depends on how we're going to do it. We need to know what the moisture contents in situ and all that is. This will also determine the technique, whether it's mix in place, or I should say mix on site, or inject. That will determine that as well. So, and then we'll provide specifications. That's the one thing I didn't bring. My sort of right hand over in Denver, she never wants me to give out the specifications unless somebody's serious, because I lay out the whole thing. I mean, that's what I should have brought, because then you could really see exactly how we specify the whole thing. And if you ever want it, just call me. I'll give it to you. But it explains the specifications, methodology of applications, and all that in one document. And then we help them develop performance criteria. With performance criteria, on injecting for houses and things like that, we normally use elevations. And I think roads would be great using elevations as well, if you're injecting, because you're really seeing whether it's going to work or not. You know, instead of taking a boring, and doing ring samples, you know, which, you know, if you've got an injection here and injection over here, you might have to wait 6 months or so before it gets more distributed evenly. Whereas in new construction, where we over excavate and then come back in, that's where we use, we bring it back in, bring it up, you know, every lift, every 8-inch lift, we'll be taking ring samples after we compact it. And we normally try to use rubber tired rollers like on front end loaders or scrapers or whatever. I like those better. You know, it maintains the structure a little bit better, that flocculent structure. But if we're into like clay stone, mudstones, then we use the sheep's foot, because it breaks it down so much better. It breaks it down real well. And so then let's see, where's the next one here? Okay. Same recommend. Yeah, okay, so we're going on here. Yeah, so all these soil conditions will affect how we recommend how to do it, which is important. I mean, you know, we want to get it right. And all right, let's go on to the next here. All right, let me get out of this. There's another file here. You gotta be kidding me. Is it working or? This doesn't seem to be. What's that? No, it isn't. I'll just we'll just go through this like this, and I'll use the. Where'd my thing go to? Laser. This is what I normally use. It's a lot easier for me to use the laser. I'm not used to working off this too much. So for new construction, I'll show you some jobs we've been doing. New construction here, mixing operation with ionic clay stabilizer. And this is it's called the Commercial Lofts near Cheyenne and Clayton in North Las Vegas. And this is the one we did a 15-foot over-X on this due to the soil conditions, and perch water tables and things like that, and swell pressures. And I wasn't the geotechnical engineer, so I didn't recommend that. Somebody else did, but I took all the samples, and we tested these. I mean, a tremendous amount of data, and you'll see this in a moment. Okay. Son of a gun. It's not moving here. You know, this isn't working here. Yeah, maybe I'll do that. I'll close it. Let me get up here. No, I'm not even getting this thing to move here. Yeah. Doesn't come off that. What if we hit resume slideshow? it's the second one. The second one, yeah. Oh, there we go. Okay. There we go. Okay. Sorry about that. Okay, so we're going to look at some of these here. And this project here, we had some big dozers out there ripping it up, and we went down, like I said, 15 feet. But before we did the 15 feet, before we did that, we went out with a backhoe in about 15 different places. We dug down 15 feet and took samples every foot going down, bag samples. So I'll explain that later, because those are going to be the untreated ones that we compare at a later point. So we did that ahead of time. It was a lot of work. It wasn't that much work, but you know, we did that up front, and then we started into it. And typical grading operations, scrapers and dozers and so forth like that. We got more of this. We're using a scraper here for compacting, I think. And now this is where we have you can see the elevated water tank up here. And we have this shed here, and this is where we're keeping the chemicals. And this is where we pump from the chemicals. And here you can see we have a meter here where we can measure the amount of chemical we're putting into the water pools. And this comes out up here, this hose right here, this hose right there is coming in here. And as it comes out the elevated tank, it comes down to the water pool and it mixes as it's going. And here we are, we're putting this on with a big water pool. And like I said, we're doing dust control, always make sure the chemical's in it. Don't ever do dust control without it. But this is obviously being applied to the clay itself. A few isolated areas we hit with that. And then this is the key piece of equipment, this disc. Like I said, it's being pulled by a D8. And it really processes it nicely. The only thing that will be better is a reclaimer. You'll see one of those in a moment. And that's the key thing, is that disc, to have that on the job. And here's more showing here. With those discs, you can get into a corner with them pretty well. Surprisingly, you can just put the wheels down and back up and lift the wheels and, you know, keep doing that. It goes fairly fast, even in a corner. And here's the motor grader. We just use that to, you know, level things out, rough grade type of thing. We weren't really processing with that. And in this case, we're using the front end loader for compaction, because I like the big rubber tired wheels. They tend to leave more of a flocculent structure in the clay. And that's important, because once you get that flocculent structure, you don't want to disturb it again. You disturb it, you remold it. Now it tends to go back to a dispersed structure again. So okay. Here's the results of this. And this is the most important thing I'll show you probably, actually. This is you can see here, this is treated, undisturbed. These are all the ring samples we were taking. Every single time we put down an 8-inch lift, after we put the chemical in and compacted it and all that, we take ring samples. And we had so many ring samples, it's unbelievable. And with a hand sampler, you know, so every single lift. And then when we come back at 21 days, we were actually testing those in swells. This is treated undisturbed swell tests, the ring samples at 21 days. And as you can see, the percent swell was 2.4%. Now realize, this is under a 60 PSF surcharge, only 60 PSF. That's a very large surcharge, real low. But that's what Clark County does over there in southern Nevada. All southern Nevada, they have to use this 60 PSF. It's a standard requirement. If this had a 500 PSF or 1,000 PSF, it would be less than 0.5% swell, easily less than 0.5%. But with this, it's going to be, 60, it's going to be a little bit more swell. Now you look down here, the untreated, remolded swell tests. This is untreated. And how we did that, we took all those samples we had before, and we compacted them to the mean dry densities of the treated ones, this 95.6 and moisture content of 22.5. So down here, we couldn't get it exact, but we're pretty close. And then we tested those untreated. So those are remolded, no chemical in them. We compacted the same density and moisture content as the treated, so exactly the same moisture content density. And of course the treated were undisturbed, but these were disturbed, but untreated. And as we see, untreated is 20.4%. That's, a big difference in swell. I mean, that's 700 or 800% more swell than the treated. But probably the most important thing here, I mean, that's important, obviously. I don't want to say that. There's another thing here that's very important that you'll see, and that proves to you that we're just not moisture conditioning this stuff. This is what we're accused of sometimes in Denver and California a little bit, but you're just moisture conditioning, and you're just adding water to it. That's all you're doing. Well, take a look at this. This down here, this is the untreated one. The pre-swell moisture content right here is 23.9%. Now look, oh, by the way, look at how many samples we did on this. 96 samples, 96. This is 73 on the untreated. And there's more I'll show you in a moment. But look at this, on the untreated, the pre-swell moisture is 23.9. Look at the post-swell is 40.9. That's significant, it's over 70% increase. Look here on the treated. This is the key, really. This is amazing. This pre-swell moisture is 22.5. The post-swell is only 27.2. It added some water, it's not totally saturated, so it's gonna take some water up just to become 100% saturated. But that's major, whereas down here we're going to 40.9. And so that proves to some of these geotechs that keep saying that they like to do moisture conditioning all the time, that it's not just moisture conditioning, it's really stopping this thing from swelling. Because if we really did this, they'll go out there and they'll inject in these areas, sometimes they'll over-excavate moisture condition, but that's crazy because they can only get up to about 5% above optimum, and you can't get compaction when you go back in. So they'll come in with these big rigs, and I'll have a photo of it, these big rigs in Texas and Colorado, and they'll inject to bring the moisture content up, and they might bring it up to 40 or 50% or whatever, and just injecting. And, that's, but it's going to swell. This is before construction, so it's going to swell. Now with time, that starts drying out. What's going to happen? It's going to be going down. But this right here, it's not going to be going down much. There's not going to be much difference here. And I'll tell you, that's the biggest thing in clays. Sure, we have hydrocollapsible silts, we have soluble gypsum for soils, we have all these collapsing type features or soils problems. But with clays, and they might collapse a lot more, than these clays swell. But the difference between the clays and why they cause more damage than anything else is because they keep going, they're cycling. And so every season, they're going like this. And every season, the crack gets wider and wider and wider. And that's really, you might not see that much swell. It might only be 2 or 3 or 4% swell, but you've got this constant cycling. That's what really causes clay problems more than probably anything else. So anyway, the point is here I'm trying to make is that we're not moisture conditioning. We're nailing it, right there. This is a heck of a lot of data here. I mean, really, I did a lot of data on this. Here, this shows here the same figure here. And it just says ionic treatment is not water conditioning the clay soils. And ionic stabilized soils at near moisture content is really about 3 or 4 or 5% above optimum content before my assistant put that together. Swell tests show only 21% increase in moisture content in addition. Oh shoot, I got to hustle here. The same soil, starting at virtual, the same soil, showed 71 increase and about 750% increase of swell potential. But this next one, this is real important too. I did 37 3-day tests and 37 21-day tests. And this is 3-day tests, 21-day tests. And you can see when you let it sit there, and it just gets better and better and better. It keeps getting better because the 21-day test has even a lower swell potential than the 3-day test. And let me go through this. I'm not going to show this is some of the buildings. There's no cracks in it, nothing. Just we don't have enough time to go through that in much detail. So let me just get through this. This is the Progressive Insurance job. I was a geotech of record on this one, and this is the same thing. We did the same thing on this, and we got real good results. We didn't take as much data on this, but you can see the results right here. This here is swell for the untreated right here, and this is swell for the treated. And it goes from 13 to 0, 11 to 0, 15 to 1, 16 to 1, 10 to 0. And, so it's very good results. And this building here, I mean, it's a monster. I mean, I've been around that many times. I look at that thing over the years. This is about 8, 9 years old. And there's no cracks. I mean, just, perfect. And that's, the water table is about 11 feet here, if I remember right. Yeah, 11 feet. So, I mean, there was real problems. There's some pretty, serious clays there. But we have no problem whatsoever. It's just solid right there. And then here's a reclaimer I was telling you about. This is a great way to process it. I mean, a really good way to process it. Got these teeth. Oh my God, this thing goes like anything. The asphalt zipper is just a smaller version of this. But, here's the rigs here. In Colorado, they got this. And they're on a frame, and they got 6 of these wands going down in there. And they can do 6 at a time. And they keep on going across. As you can see, they got trucks and trailers following. This is some work done years ago in Arizona. I'm not going to go through that at all. Yeah, I think that's. Is there any questions? Anybody have questions or? Yeah. For clay swell, the best indicator is the swell test. I mean, you can do Atterberg limits evaluate the untreated, soil with Atterberg limits, the liquid limit, plastic index and all. But for the treated soil, you don't want to use Atterberg limits because whenever you do an Atterberg limit, you have to remold it, so you're breaking that structure down. You're losing, I see it all the time. People try it and it doesn't work out. Well, that's why. It's breaking the structure down. But for just finding a clay soil that's bad, the Atterberg limits, is a good way to do it. The classification system, including the Atterberg limits. But really the best way, if you have the ability, is to do a swell test. And if you're in the field and you've got these little hand samplers, they're pretty convenient. You just drive